You are listening to The Vocal Technologist. Spoken tech for your ears.
So look, picture this. You have got a highly sensitive message on your phone.
Right.
You're using a secure, encrypted messaging app. You read the message, and then you do exactly what you're supposed to do. You hit delete. The app promises you it is gone.
As it should.
Exactly. In fact, to be extra safe, you completely uninstall the app from your device. You would think that data is just vaporized.
You would certainly hope so.
But what if I told you that months later, the authorities could just plug your phone into an extraction tool and pull that exact deleted message straight out of thin air?
It sounds like a straight-up violation of physics. Or, well, maybe broken encryption.
Yeah.
But the reality is actually far more mundane and honestly much harder to fix.
Yeah.
It is a quirk of how mobile operating systems handle information routing.
And look, this is not some hypothetical thriller movie plot. The FBI has successfully used extraction tools to pull supposedly deleted signal messages right out of iOS push notification databases.
Yeah, the push notification system.
To understand why this happens, we have to look under the hood of how Apple actually delivers a notification to your screen. Because when someone sends you a message, the data does not just flow directly from their phone into the app on your phone.
No, that direct path is a really common misconception.
Yeah.
The data actually goes through a central hub first.
Right.
It flows into the push notification servers run by the operating system vendor, so Apple or Google. Those servers then wake up your specific device and deliver the payload to the local operating system.
And the crucial step is what happens next, right?
Exactly. The operating system logs that entire notification in a central system-level database before handing it over to the specific app you are using.
Oh, wow. So even when your ultra-secure messaging app does its job perfectly and, shreds its own internal database, the operating system is just sitting there holding the receipt.
Holding the receipt in plain text.
That is wild. The plaintext message just persists in the system logs entirely outside the control of the app you used to send it, and it stays there even after you remove the app from your phone entirely.
What is genuinely fascinating here is how security boundaries just completely break down when different complex systems interact. I mean, you can build the most secure fortress in the world, but if the local council insists on keeping a public registry of everything that passes through your front door, well, your privacy is compromised by design.
Spot on. Which brings us to the immediate real-world fix for anyone listening who wants to lock this down. Because there is a fix.
There is, but you have to do it manually.
Right, you have to go into your iOS settings and set notification previews to never. And crucially, you need to go into the secure app itself and disable notification content from being sent to the lock screen. You basically have to starve that incoming payload of any actual data.
Yeah, it forces the app to just receive a generic wake-up ping, meaning the operating system database only records that a message arrived, not the actual contents of the message itself.
Okay, let us unpack this, because that sets the mission for this Web3 Wednesdays InfoSec edition. We are going to explore how the foundational layers of our digital trust are just being quietly dismantled.
Layer by layer.
We are moving from the devices in our pockets to the global infrastructure running our hospitals and power grids. We will get into $10 domain blunders that bypass millions of dollars in cyber defense. We will talk about artificial intelligence autonomously rewriting the rules of exploitation.
Which is a massive shift.
And we will pull apart the quantum mathematics threatening to break the internet entirely.
Look, the overarching theme we are seeing here is an escalating collapse of trust. The assumptions we have relied on historically are simultaneously failing across multiple fronts.
Speaking of the collapse of trust, if you think losing private messages to a hidden notification database is a dodgy technical oversight, enterprise infrastructure is currently failing for reasons that are, frankly, embarrassing.
Oh, the update domain incident.
Yes, I am looking at the unregistered update domain incident. It is pure absurdity.
It is a perfect case study in how fragile corporate networks truly are.
So here is where it gets really interesting. There is a browser plugin, widely used across major enterprise environments, and the developers behind it simply forgot to renew one of the web domains they used to push software updates.
They just let it expire.
Just let it lapse. So a threat actor notices this, swoops in, and buys the domain for about $10.
Which instantly grants them ownership of the exact infrastructure that 25,000 enterprise endpoints are programmed to trust implicitly.
Just for a $10 fee. Picture operational technology networks, healthcare providers, government systems. All of them are constantly pinging this cheap $10 web address, asking for new code to run.
And the attackers just stand there saying, "What? Yes, please execute this new payload."
But the execution phase is what I want to pull apart here because it relies on Windows Management Instrumentation, or WMI. Let me see if I can explain this clearly. WMI is essentially the central nervous system for managing a Windows environment, right? It allows administrators to query system information and run scripts across a network.
That is a highly accurate way to describe it. It is an administrative tool built deeply into the operating system. It is meant to be helpful.
So the attackers push a payload that uses a PowerShell script to hijack this central nervous system. They use WMI to establish persistence, meaning the malware survives a reboot, and they use it to silently disable the antivirus software.
But the truly brilliant part is where they hid the subsequent malware payloads.
Oh, yeah, this is wild. They drop them directly into folders that Microsoft Defender actively ignores by default.
Because defenders have to configure antivirus software to ignore certain administrative folders. Otherwise, you get false positives that break legitimate IT processes.
Right, so the attackers just...
They simply read the public documentation for Microsoft Defender, found the default exclusion paths, and parked their malicious files right there.
It is like sneaking into a maximum security prison by wearing a guard uniform and just standing in the one corner where you know the security cameras have a blind spot. I find this genuinely hilarious in a very dark way. You have these huge organizations spending millions upon millions of dollars on command centers and threat intelligence feeds, and they get entirely compromised because someone forgot to put a domain renewal on autopay?
It happens more than you would think.
It is like spending a fortune on a 2-ton titanium bank vault door, complete with biometric scanners and laser grids, and then just leaving the master key under a cheap plastic welcome mat.
Well, it illustrates the reality of supply chain vulnerabilities perfectly.
Yeah.
Attackers rarely bother trying to smash through that titanium vault door anymore. They look for the trusted vendor who brings the coffee inside the vault every morning.
Yeah.
We saw the exact same methodology play out with the CPU-Z and HW monitor breach.
Oh, man. If you are a PC builder listening to this, you almost certainly know those names. You probably have those utilities on your machine right now to check your processor speeds or system temperatures. We just inherently trust them.
And that absolute trust makes them the perfect vehicle. Attackers breached the company via a compromised side API and managed to hijack the download links on the official website.
So the actual official links.
Yes. For about 19 hours, anyone attempting to download those legitimate utilities was handed a Trojanized installer.
And the mechanism of infection here is fascinating to me because it did not just install a virus directly. It used a technique called DLL sideloading.
Correct.
Let me break this down for a second. Windows applications usually rely on dynamic link libraries, or DLL files, to function. These are basically helper files containing code that multiple programs can share. So when you launch the legitimate CPU-Z application, it looks around its local folder for a specific helper DLL to load into its memory.
Because the application assumes that any file sitting next to it with the correct name is trustworthy.
Exactly the blind spot. The attackers slipped a malicious file into the download package and gave it the exact name of the file the legitimate application was looking for. So the trusted application reaches out, grabs the malicious code, and executes it with all of its own trusted privileges.
And it bypasses sandbox detection beautifully.
Because the security software just sees a verified, digitally signed application asking to run code.
Exactly. Once loaded, it deployed the STX remote access Trojan. This gave the attackers full in-memory execution capabilities and reverse proxy tunneling straight into the victim machines.
So the very utility system administrators use to ensure their machines are healthy become the weapons used to compromise them. But hang on, once attackers get in through these cheap mistakes or hijacked downloads, they still need a way to maintain control, right?
They do. They need command and control infrastructure to send instructions to the infected machines.
And traditionally, that is the weak link for any cybercriminal. Security researchers or law enforcement track the malware back to the servers hosting the command infrastructure, and they work with hosting providers to just pull the plug. The infrastructure gets seized, and the malware is neutralized.
Right. Enter Omnistealer.
Yes, Omnistealer. This is a piece of malware that has decided to leverage the blockchain, and it is honestly a stroke of evil genius. We need to look under the hood of how this operates. Usually an infected machine reaches out to a standard web address, to ask for its next set of malicious instructions.
But an omnistealer abandons the traditional web server entirely. Instead, it embeds encrypted staging code directly into public blockchain transactions on networks like TRON, Aptos, and the Binance Smart Chain.
And the reason they use those specific networks is brilliant. They have incredibly low transaction fees and high throughput, so the attackers can embed their encrypted instructions into the public ledger for fractions of a cent.
And if we connect this to the bigger picture, the impact is devastating because public ledgers are append only by design.
Right. Meaning you cannot delete a transaction. You cannot call up the administrator of the blockchain and ask them to remove a malicious file because, well, there is no administrator.
The entire point of a distributed ledger is immutability. Defenders and law enforcement literally cannot take the infrastructure offline.
That is wild.
The command and control mechanism is permanently baked into the public record. The infected machine just queries the blockchain, reads the specific transaction hash, decrypts the instructions, and executes them. It is an unkillable command post.
Which is just a dry, beautiful irony. The tech bros spent years trying to find a flawless, world-changing use case for the blockchain, and it turns out the ultimate application is bulletproof malware infrastructure.
It is quite the pivot.
Because apparently that is where we are now.
And look, it is highly effective at scale. Omnistealers targeting over 60 browser-based crypto wallets and numerous password managers. The researchers tracking it estimate it has compromised roughly 300,000 credentials, hitting everyone from financial firms to defense suppliers.
Just heaps of targets.
Oh, absolutely. And it relies heavily on fake freelance job offers on platforms like LinkedIn to trick victims into downloading the Trojanized code repositories in the first place.
So human attackers getting clever with append-only ledgers is one thing, but finding the cracks in the vault door has historically required a human being to spend months staring at complex code.
Yes, very labor-intensive.
But what happens when artificial intelligence starts finding the vulnerabilities for them?
Well, this raises a really important question about the future of defense. We are transitioning from AI, just assisting attackers with writing generic phishing emails, to AI autonomously discovering novel exploitation paths in legacy systems.
The Apache ActiveMQ situation absolutely blew my mind. Let us get into this. ActiveMQ is a hugely popular open-source message broker. It helps different applications communicate with each other across a network. Researchers aimed the Claude AI model at the code base, and Claude discovered a critical remote code execution vulnerability that had sat completely undetected in the software for over a decade.
13 years, to be exact.
13 years.
A 13-year-old logic error just hiding in plain sight.
Let me explain the mechanics of what Claude actually found. During the initialization process of the software, there was a flaw that allowed an attacker to force the broker to fetch a remote configuration file from an external server. The system would then blindly execute arbitrary commands contained in that file.
Very dangerous.
And Claude not only identified this obscure logic error, but it wrote the initial proof-of-concept code to trigger the crash.
Because it understood the complex interaction between different components of the software and synthesized a path to exploit it.
But let me push back here for a second. We have all used these language models. They confidently invent completely fake information all the time. They write code that looks beautiful, but completely fails to compile. Is AI just going to get stuck hallucinating broken exploits, or is this a genuine crisis? Are we saying every boring, unpatched office printer sitting in a corporate hallway is now a massive security liability?
It is a genuine crisis.
Yeah.
And yes, your office printer is absolutely a liability now. The hallucination problem you mentioned is actively being solved through what we call agentic workflows.
How does an agentic workflow actually operate?
Well, instead of asking the AI to write an exploit in one shot and just hoping it works, you give the AI an environment to practice in.
Okay.
The AI writes the code and runs it in a secure sandbox. When the code inevitably fails or hallucinates, the system captures the error messages in the stack trace, feeds those errors back to the AI, and tells it to fix its own mistakes.
So it is learning from failure.
Exactly. The model iteratively rewrites and tests the code hundreds of times a minute until the exploit functions perfectly.
It is a self-correcting loop, and we have concrete proof of this from the UK government tests, right?
Yes, we do. The AI Security Institute took Anthropic's Mythos model and dropped it into a highly complex network data exfiltration exercise. We're talking about a 32-step cyber range.
32 sequential steps.
Yes. The AI had to map the network, compromise initial systems, figure out how to pivot laterally through internal servers, escalate its privileges to an administrator level, locate the sensitive data, and exfiltrate it without triggering the alarms.
And it did all that.
The model successfully completed the entire 32-step chain autonomously. It adapted to roadblocks without human intervention.
That is staggering. So what does this all mean for the industry moving forward?
It means the economics of exploit development have entirely collapsed. Historically, finding a reliable vulnerability in a major enterprise system required a team of highly paid elite researchers reverse engineering code for months.
We are talking about moving from an artisan blacksmith hammering out a single beautiful sword over 6 months to building a fully automated robotic assembly line that just churns out thousands of weapons a day.
That analogy captures the severity of the shift perfectly. Because the cost of finding vulnerabilities is dropping to near zero, attackers no longer need to carefully pick high-value targets.
They can just cast a huge net.
Exactly. They can simply aim autonomous coding agents at the vast sea of legacy software that runs the physical world. Regional bank infrastructure, hospital management systems, industrial control protocols. The agent will just patiently poke at it millions of times, learning from every single failure until it finds a way in.
Which means the defenders are now fighting an automated adversary that does not sleep and costs pennies to run. Which, yeah, is exactly as terrifying as it sounds.
It really is.
But look, while artificial intelligence is actively breaking the logic of our software right now, we have an even larger structural problem approaching. Quantum computers are quietly gearing up to break the underlying mathematics that secure the entire internet.
We are looking at a shrinking quantum time bomb. The security of the modern web relies heavily on elliptic curve cryptography.
Let us unpack the math here without getting too dense. The internet essentially uses trapdoor functions, right? Mathematical problems that are incredibly easy to calculate in one direction, like multiplying two massive prime numbers together. But they are almost impossibly hard to reverse engineer, like taking that final massive number and figuring out which two primes created it.
And classical computers would take millions of years to crack those numbers. The assumption has always been that it would take a massive, highly stable quantum computer to break that math using something called Shor's algorithm.
But the timeline for those machines existing is accelerating.
Drastically accelerating. A paper from Google demonstrated that elliptic curve cryptography can be broken with significantly fewer logical qubits than anyone previously modeled.
Wait, let me make sure I've had my head wrapped around this distinction because it is vital. A physical qubit is the actual raw hardware component in the quantum machine.
Yes.
But they are incredibly fragile. They are prone to interference from things like temperature or stray radiation. So to get reliable calculations, you have to group a huge number of physical qubits together to create one stable, error-corrected logical qubit. Is that the mechanism?
You have nailed it. And the security industry assumed we would need millions of physical qubits to create enough stable logical ones to crack our encryption. We thought we had a comfortable buffer of perhaps 10 to 15 years.
Right, time to prepare.
But a separate paper from Oratomic showed that specific encryption curves can be broken with as few as 10,000 physical qubits using neutral atom architectures.
Oh, wow. Meaning the hardware required to crack the foundational math of the internet is much closer to reality than we thought. But here is where it gets really interesting. The security industry has been highly focused on the risk to data in transit. The fear that adversaries are scraping encrypted internet traffic today so they can decrypt it tomorrow when a quantum computer comes online.
Look, while that store now, decrypt later scenario is a valid concern for highly classified state secrets, it is a massive distraction for the broader enterprise environment.
Why is that?
The real crisis approaching us is authentication.
Authentication.
Authentication relies on digital certificates. It is how your computer knows that a software update is legitimately from Microsoft or Apple, rather than a malicious actor. If a quantum computer can break the math securing those certificates, an attacker can forge digital signatures at will.
Oh, wow. Okay, so if you can forge a signature, you can push a malicious software update to millions of devices, and those devices will blindly install it because the mathematical signature checks out as perfectly valid.
Exactly.
A broken certificate turns every secure software update pipeline into a massive remote code execution vector.
Precisely. It is not just about reading old secrets. It is about actively taking over the infrastructure. And we see this perfectly illustrated in a critical flaw discovered in the Wolf SSL library.
I saw this. 5 billion devices affected globally. How does the Wolf SSL flaw actually function?
It comes down to an incredibly subtle implementation error. When a system verifies a digital signature, it hashes the contents of the certificate to create a fixed-length digest. The Wolf SSL library was missing crucial checks for the size of that hash and digest during the verification process.
Let me translate this. It is like a bouncer checking a fake ID at the door of a club, but because the ID only has your first initial instead of your full name, the bouncer's brain just glitches and waves you through.
That is exactly what happens mathematically. Because those size checks were absent, an attacker could submit a forged certificate with an artificially undersized digest.
Right.
The library would process the undersized digest, the math would falsely align with the expected parameters, and the system would accept the forged certificate as entirely valid.
Even though the certificate was complete garbage.
It bypasses the core verification for multiple modern cryptographic standards. And because Wolf SSL is embedded in billions of smart devices, routers, and applications globally, all of those systems were suddenly willing to accept forged credentials without a second thought.
So we are sitting here trusting the digital concrete, protecting 5 billion devices, and it turns out it is actually just painted cardboard right at the exact moment the bank robbers are inventing a much better quantum drill.
It is a sobering realization. The foundational mathematics we use to prove identity and trust are becoming fragile, and the tools attackers use to exploit that fragility are becoming autonomous.
Let us bring all these threads together. We have explored how push notification databases silently hoard your deleted messages, proving you cannot always trust your local device. We have seen 25,000 enterprise endpoints compromised because of a $10 domain lapse, proving you cannot blindly trust your vendors. We have got Omnistealer building unkillable command and control servers on public ledgers. We have artificial intelligence iterating on its own mistakes to autonomously discover decade-old blind spots. And looming over all of this, the quantum computing advancements that threaten to shred the mathematics holding our digital certificates together.
When you look at the progression sequentially, it really highlights how the concept of a secure perimeter is entirely obsolete. The threats are no longer just battering against the outer walls, they are embedded in the infrastructure itself.
Which leaves me with one final thought for you to chew on. We spend billions trying to build secure environments and patch logic flaws. But if AI agents can autonomously find vulnerabilities we missed for 13 years, and quantum hardware is poised to casually unravel the foundational mathematics of our digital identity, are we entering an era where building a truly secure system is not just difficult, but mathematically impossible? Stay curious, stay paranoid. You have been listening to Vocal Technologists.
Spoken Tech for your ears.